All right, we are good now. um, okay. Uh, so um, number 4 is digital redesign. Basically, this is where we try to connect a discrete time controller into a continuous time plant, right? Pretty much every control system in the world, right? So almost all of them, the plant is actually continuous time, whereas the controller is discrete time, right? So we'll see what are the additional modifications we need to bring in to connect two different systems. One is discrete time, the other one is continuous time to work together. Then we are going to look at aliasing and frequency warping. So what is that? When we deal with control systems, we generate control signals. A signal is a time domain signal, but it's composed of multiple frequencies, right? Sometimes so many different types of frequencies in there. So as we saw in the first semester, the body analysis, we looked at how these frequencies travel from input side to the response side, right? So, and uh, depending on how easy or how difficult all these frequencies transfer to the response side with phase lag and all, right? You get a certain response, and then you judge whether the response is acceptable or not, right? Um, but that is one thing. But here, there's more important things to be discussed, like, for example, aliasing. This is actually happening because of your discretization of the plant. Okay, so to discretize the plant, you bring in new components, namely holding circuits, samplers, right? And you actually distort the frequency spectrum more than what is naturally happening in any plant, any system, when the frequencies travel from one end to the other. Okay, so the moment you bring in the discrete components, right, the frequency propagation changes further. So therefore, you need to look at what are these additional effects, right, and control them. So that is number 5, aliasing and frequency warping. Number 6, state space modeling. This is uh, another way of modeling, right? In the first semester, uh, we looked at the basic mathematical modeling of a plant or a system, right? Remember shock absorber, RC circuit. We used the laws of nature, right? Like Newton's laws, Kirchhoff's, right? And we got the differential equation that described the plant dynamics, how the plant changes, right? Um, Now, if you look at the RC circuit, we got a first order differential equation. And for the shock absorber, we got the second order differential equation, right? And for complicated systems, you might get third order, fourth order, fifth order, high order systems. And now this is going to be an increasingly difficult problem to handle, the differential equations of higher order. Now in mathematics, in engineering, one of the frontline technique to handle complex problems is to divide and conquer. So you break the complex problem into a number of small problems which are not that complicated, right? So that is the approach in high order differential equations, right? So plants with high order mathematical models, right? If you want to analyze it, right, and you find it difficult to deal with it with that higher order model, you can break it down to a small, uh, mm, um, say, first order differential equations, but many of them. Okay. Say, for example, if you have fifth order differential equation, you can break it down to five first order differential equations. So dealing with five differential equations that are all first order is much easier than dealing with the fifth order differential equation right away. So this technique is actually developed in 1970s, and the name given to it is state space modeling, right? Richard Kalman and others in that time developed this new way of modeling. Is actually not a truly new way of modeling, but it is a remarkable thing, right? To see how the differential equations are actually written in a set of first order equations, and then can combine them together like a stack, and gave it a name, state space model. And using that model, can you do all the things that you usually do in control systems using transfer functions? Well, yes, and you can do even more than that. Like, for example, observability, controllability, right? Um, One of the things you need to know about the plant you are dealing with is whether the plant is observable, which means whether you can use the response that you measure, right? Uh, and measure it, keep measuring it for some time. Now you have a data sequence. Looking at the data and looking at the plant dynamics, can you observe or estimate other things about the plant? Okay, because there's so many things in the plant. Let's call state variables, right? Uh, can you calculate or estimate all of the state variables, right? Looking at the response, so a few measurements. So you use few measurements and the plant dynamics, and you estimate the other things of the plant. So this is what's called observability. Some plants are observable, which means you can actually estimate the states, right, with the output and the plant dynamics. But some plants are not observable, which means you cannot do that for such plants. So they're not observable. Then the controllability. Controllability is, can you use this single control signal and control all the states in the plant. States means, say, if it is a vehicle, the speed of the vehicle, the acceleration of the vehicle, the position of the vehicle, right? Or the steering angle of the vehicle. Can you estimate all of these things, right? Using a fewer number of measurements, right? Um, so if the plant is controllable, the answer is yes, you can do that. But if the plant is not controllable, which means you cannot use this control signal, right, to calculate the other states. Okay. Say one example is, let's say for a vehicle, right, going in a line, right, say your gas pedal, the pressure on the gas pedal is the control signal. You apply gas or you reduce it, right, gas pedal, and then you get the speed, you get the acceleration, the speed, and the position and all, right? Let's say you measure acceleration, only the acceleration. So can you use the gas pedal uh, control and acceleration and the vehicle dynamics? You have the mathematical model of the vehicle, right? Using these things, can you estimate the velocity of the vehicle and position of the vehicle? You might say yes, right? Yeah. So in that case, it is observable and also controllable, right? You can control the velocity, you can control the position using that gas pedal, because this pretty much we do in every vehicle, right? It doesn't mean that it's the case for every plant. There are some plants which are not controllable, right? So we want to have mathematical tools developed to check whether the plant is observable or controllable. On paper, we can evaluate that, and we don't have to do it by the hard way and learn it, right? These are new concepts developed in late 60s and early 70s by Richard Kalman. You know the famous filter, Kalman filter for state estimation. They all started during that time. And if you look at the control systems and what sort of controls we developed in the first semester, right? We looked at PID, right? And also we designed the compensators, increase the phase margin, and steady state error, etc. So you know something about controls, right? It's not just one controller like PID. Now you know there are various ways to design and build controllers, right? But all of these controllers, we actually took the response output, right? Y, and feed it back. But now, if you look at the state space modeling, second order plant has two states. First order plant has only one state, of course. Third order plant has three states, right? You will learn that. And you can measure these states or estimate these states and also feed back these states to a controller, which is not PID, or which is not a loop shaping kind of thing. This is a different type of controller, which takes multiple inputs into it and then calculate the control signal. So one such controller is state feedback controller, SFC, or another one is Lq1. Okay, so we're going to look at the state space controller and the linear quadratic regulator. So these are two different controllers which are different to PID and compensators, so that you now have, you will have after, say, at the end of the semester, a number of control systems, right? You can choose from whether you want to have a LQR or SFC, state feedback control, or stick to the classical PID and loop shaping. Okay, all right. And at the end, towards the end, we're going to look at details about the Kalman filter. It is one of the most popular state estimators in control domain. And also we're going to look at the Lec1a stability, right? Lec1a is a Russian mathematician who developed a very intuitive technique to check the stability of plants. So we're going to look at that also. So this is the content lineup for the module, digital control systems. And for the references, I don't have a single reference for this one, because I looked at all these references. These references are actually uh, big, big books, and can show you some of these things here. This is Tevari, big book, and it doesn't serve the, actually there are good contents for this module, but there are other things that I don't really want to cover in this module, and this is Kuo's book, and I pick up certain contents from Kuo, Nice, and Tewari. So I got disconnected again. Right. Okay. So we use multiple references, right? Because we want to cover certain areas that you do not find in one single book. All right. Any questions up to that point? Okay. All right. This is the control system we discussed at the end of the last semester. I want to show it to you again and to recap your memory. Right. We had the plant. Right. This is a third order plant. You can see S to the 2 and one S term here. Third order plant. Right. The 3 poles and 1 zero. We wanted to design the plant for a certain specification, right? So we put this gain to increase the bandwidth. Remember all these things? And we designed this lead compensator, right? To increase the phase margin to about 45 degrees. And then we want to increase the steady state error, right? For that, we use a lag compensator. And then suppose this whole thing is uh, the controller, right? So you know that uh, the uh, the gain that you use to increase the bandwidth and the lead compensator lag combined together is the controller. Now, if you take the controller as a block, right, from here to here, it has an input and it has an output, its own output, right? So the input to the controller is the error ES, and output from the controller is the control signal US. So if you draw or write the controller transfer function, which is US over ES, right? It will be just these 3 blocks. Okay, you have the lag compensator and the lead compensator and the gain. So once you multiply all these things and then spread it out in order to get the U, right? The control signal which is coming out of the controller, right? As a function of whatever comes on the right hand side, which is basically the error and the control signal itself, right? You can see US is over here, but US is also over here. But it doesn't mean it's the same US. It's a different US at different times, okay? So going forward, right? So now this is a Laplace domain representation of the controller, right? Or the control signal US, okay? Now, with that equation, right? What we did last time was we tried to implement this. Okay, we tried to implement this using an analog controller, right? Using an analog controller. Uh, so we were able to do that with a number of differentiators, adders, subtractors, and so on and so forth, right? I think you're pretty skillful about it, right? Once you're given a equation like this, you know that this is S times US, this is rate of change of US, and this is S square That is the rate of change, the second derivative, and so on. So signal derivative or differentiation and addition, multiplication, they can all be done using op amps. So you can go ahead and design the controller in continuous time using uh, components like resistors, capacitors, inductors, etc., together with op amps. Okay, so that was fine. But if you want to do a digital implementation, discrete controller, you need to get rid of these S terms. S are differentiation. Okay, S to the 2 is 2 differentiations. So you need to replace these S terms with some approximate or numerical approximations of the differentiation. And of course, you know that it's also very easy. If you want to get the first derivative, it is y minus y t minus 1, right? Which is last time, previous. If you get the samples now and the sample the last time you read it, you get the difference divided by time. So that is differentiation. And second derivative can also be done in the similar way. Eventually, you don't have, you will get rid of the differentiation altogether, but what comes in is samples. What is the error now? What was the error a step ago? What was the error 2 steps back? What was the error 3 steps back? Like that. You want to maintain these samples. Okay. So after that, it's about combining samples, addition, subtraction, multiplication, right? Division by time, like that. So that is the controller. It's a pretty simple mathematical computation, right? To compute the control signal using the previous control signals and the previous errors and the present error. Okay, by combining all these things in a mathematical combination, you can calculate the control signal. Right. So here on this slide, what you see is this conversion, continuous time plant, which is over here, and we convert it into a discrete version of it. We do not transform the whole thing from continuous time to discrete time, but we convert or transfer or transform rather the controller only. Okay, now here you can see the plant and the actuator. We model them together using a differential equation, right? Is still there, GS. The plant remains unchanged, okay? But we put a sampler here, right? So the response side of the plant, we have a sampler, which will give you samples like YK, right? At regular intervals of T. Every capital T, capital E is a sampling interval here. So the sampler will get you a sample, right, of the response every time T. Okay, and that is what is going to be fed in here with the reference signal. You can see here RK plus 1, which means the new reference. What is the reference now? Right? If you put your, say, air conditioner at a certain temperature, it's not going to change for some time, right? And RK plus 1 will be equal to RK is equal to RK minus 1. For all these K minus 1, K minus 2, like that, it remains the same quantity, right? But whenever you change it, you get RK plus 1, which is different from RK, right? Whatever comes in as your reference at that moment of time is RK plus 1, is the new command, okay, new command. And in a discrete controller, your R is actually RK. K is a number, 0, 1, 2, 3, 4, 5, like that. So R0 means the reference signal at time 0. Then R1 is the reference signal at time 1. What is time 1? Time 1 means after one sampling interval from 0 to 1, then 2, then 3, 4, 5. These numbers, they don't have any unit in it. right? But you have to understand that this k, an integer, which tells you the position on the timeline, that discrete signal position on the timeline. If you say R10, which means 10th sample, okay, of that signal. So when you get the difference, you get EK, that is error, again discrete, okay, again discrete. It goes to the controller. And now if you look at this controller here in the continuous time form, which is CS, which is very familiar to you. Now we don't write it like CS, we write it as CZ. You know, this is different, right? This is a discrete controller. That is why we call it CZ. Whereas the continuous time controller, we give it CS, which is coming the Laplace transform of the controller. Still, you do not know what this is, right? What CZ is, you do not know, but you can at least understand, because if this is a discrete controller, it cannot be CS. Then what should it be? Should be something else. For the moment, we call it CZ. Okay, right. So this, what the CZ does is, it implements this equation here, controller equation, not actually this one, the discrete version of this one, okay, discretization. I think last semester you did this discretization, okay, you took out all the different differentiators, s square and so on, and then replace them with approximate numerical expressions, right? So that equation is what is implemented here inside CZ, and it generates UK. Okay, generates UK. Now, this discrete mathematical operation, right? It's not very physical. It's not a physical thing, right? It's just mathematical equation. You have few numbers here and few parameters here. You combine them together and produce another number. Okay, just a number cannot control a plant. To control a plant, you need to convert it to a signal and actually latch it. Latch it means you have to provide continuous power to the plant, right? Which is corresponding to the control signal number that you calculated, right? So for that, this UK signal has to stay there, right? From this moment of time to the next moment of time, because within that time, your controller does not do anything, because it's a discrete controller. It calculates the control signal and gives out that control signal, and after that it goes to sleep for one capital T time, okay, whole sampling interval. It doesn't do anything. So the signal the controller calculates, you have to send it to a zeroed hold, meaning that it holds that signal for one sampling interval, capital T, okay? And therefore, for that period, the control signal remains UK without changing it, right? This UT is equal to actually UK for one whole period. So after capital T time, the controller will create the error, okay, because it is the difference between RK plus 2 now, and this is YK plus 1, right? After sampling interval, it will have EK plus 1, new error. Therefore, the control signal is also different, UK plus 1, right? And the time, the continuous timeline, you hold a different value. It can be bigger than the previous value or smaller than the previous value. So this way, you can properly operate a continuous time plant and control it with a discrete time controller. So all what you need is two components, okay, two blocks. One is the zeroed hole, the other one is the sampler. And you also need to know how to develop the CZ. Okay, CZ is coming from the controller equation. This one, once you discretize this, That is also not very difficult, because once you define these s's, s squares, and so on, and write the approximate expressions for s terms, s square, and so on, you know what it is. All right. So the summary up to now is that um, control systems are inherently in continuous time because the plants are continuous, right? But we want to, we prefer to have a discrete controller, which is microprocessor based controller, right? Then we need to convert our controller that we normally design in MATLAB and using other tools in continuous time into discrete time. Okay. And when you practically implement the discrete time controller on the continuous plant, you use zero order hold, and the sampling. Is everything clear up to now?
Yes, sir.
Any questions? Is everything clear?
Yes, sir.
Okay, good. Right. And now I want to show you some of these signals. I think I have shown you earlier also, right? This is what the sample is doing. By the way, the discretization is, in very simple terms, is this. T is replaced with KT, right? T is the continuous thing, right, which is going for the entire time, right, without any gaps or anything. Whereas KT uh, is discrete thing. K equals 0, you have the value. And K equals 1, you have the value. In between, you don't have anything, okay? And K equals 2, you have a sample. So they are just numbers, right? They are just numbers, discrete signals. Like what you see here, this is YT and YK. This set of arrows is YK. And you don't see any red thing in between because they are not connected. These arrows are not connected actually. They are standalone set of standing arrows, okay? And this is what the sampler is doing. It converts this gray signal into the set of red arrows. This is what the sampler is doing. And the other component is the zero order hold. And there you can see what the zero order hold is doing, right? It converts UK into UT, back conversion, right? These arrows, red arrows are like that, right? And it zero hold stay or keep the value at that level between samples. And when a new arrow comes in, let's say this one, it keeps that value for the next period. So this is how you convert a discrete signal into continuous signal, because this staircase thing is continuous, right? Not differentiable at these points, right? But it's continuous. So if you look at the controller at the continuous time, US over ES, it always looks like this. Always looks like this, right? What is this format? This is a rational polynomial of S. Controller is always a rational polynomial of S. Any transfer function is a rational polynomial of S. So if you go back to the controller here, this is what you see. US over ES is the controller transfer function. And on the right hand side, it's a rational polynomial of S. You see S square, S and constant term in the numerator, and the denominator is square and the constant term, right? So I think there should be S over here. Sorry about that, okay? So in general, it's a rational polynomial of S, right? So if you just write it in the generalized format like this, a0 is to the m plus a1 is to the m minus 1 and so on, over b0 is to the m plus b1 is to the n minus 1, like that, right? Don't worry too much about